10 minutes. Susa, are you there?
I'm here. There was a short network error, but I think we have recovered.
Okay. Was it on my side or on your side?
It might be on my side.
Okay. So maybe
By the
I'll
way,
ask you. Yep,
did we say how people can write questions in the notes at any time?
true. So that's the same notes document that you already were using for these icebreakers. You can use it for writing questions there. And so anything that comes to your mind, please write it there, and then we can
Yeah.
give answers.
It also gets all the links to whatever we're looking at and any notes we're sending to you. And everyone
Yeah.
you don't see on the stream is there watching that and answering your questions. So go for it. Okay, that's all.
Yes,
Thanks.
we have a big network of helpers ready. So if I ask you, Susa, what is scientific computing? How would you
Well,
answer that?
basically, I would answer that scientific computing is at the baseline everything that every part of computing that helps science, that
Mhm.
helps researchers. And then obviously you would want to ask, what is computing? And well, computing is using computers instead of pen and paper to solve your problems. So, um, solving problems with the help of computer to help research is what scientific computing is
Yes,
about.
I, I totally agree. There's this funny XKCD. Someone said that there's always an XKCD for anything related to computing or computers. And, is this your machine learning system? So, it's like a pile of stuff. And sometimes we have this maybe approach to computing that we might not understand all the bits that are happening inside the pile. So we kind of maybe have a kind of some sort of black box experience with the computing, that some data comes in and something comes out. So this very short introduction is actually trying to, you know, open this black box, and I think it's still important to get the basic. So like Susan was saying, a common scientific computing flow chart would be that that you have some data, whether it's collected data or simulations, and then there is some processing happening, and then you generate some outputs that can be statistical tables, AI model, machine learning models, whatever is the output. And then, you write papers, posters, figures, and publish and become successful and, be a famous scientist. But then what actually happens in practice, and I think this is very important because we were chatting with others that sometimes this jargon of the basically hardware that is needed for doing scientific computing is just assumed that everybody knows about everything, but maybe it is not like that. And I also think that it's important that once someone knows how the components are connected with each other, and if they're actually physically close to each other or physically far away from each other, then it can also affect, is it going to be fast? Because yes, the memory that I'm using is really few millimeters away from the mm, computing that is happening, or is it that uh, the data that I'm loading is far away in some remote server in the cloud, as they say. So what you see here in this type of stacked picture is basically that you right now, even with your laptop or with your desktop computer that you're watching this stream, or even with the phone, because the thing is similar, we have the hardware level, and inside the hardware, the physical box, there are CPUs, GPUs, RAM, SSD, and the network. So these elements, there are the definitions here, and we will not go through the definitions. Maybe this is familiar to all of you, but already if you feel that you don't know what are all these elements, then you already might be kind of missing in the moment where you will see that you request some computing resources from an HPC cluster. You are going to be asked, do you need CPUs? How many do you need? How much RAM do you need? Do you need GPUs? Do you need to use the local disk, which is this SSD here, or will you use some network disk that is not physically inside the hardware that you're using? So this type of things are actually things that you will need to think about daily when you work with high performance computing systems, but but they're basically things that sometimes you, how can I say, forget that they are always there whenever you are working. On top of the hardware level, there's the operating system that basically interacting with the hardware and then enabling the fact that on top of the operating system, you can run your Python or MATLAB or R. There's a nice little box here about containers. We will not cover those today, but basically it's like bringing another operating system with the software on top of the operating system and the hardware. So without going through these definitions that maybe some of you have, I just want to show that we have a great video series on understanding computing through the kitchen metaphor. So I will not show the video right now, but it's linked in the page. And there's in the video, there's going to be Richard with the cat, actually, that are going to basically explain how all these elements, the CPU, the GPU, the RAM, and so on, are kind of connected to each other and what it actually means in practice for your day-to-day work. There's also a set of slides with this metaphor of the parallel computing in the kitchen. And so the metaphor kind of goes, if I can cover it just briefly, we have still a couple of minutes, that each burner of a stove is like a core. It's like one of this CPU. And then the whole stove is like the processor. Then, you have the memory, which is the counter space where you can leave some of your ingredients that you need to move inside these pots on top of the burners. And then, of course, if the kitchen counter have the ingredients that are ready easily to access, you might have more ingredients that are a little bit more far away in the fridge, for example, or in some other cupboards. And then you have the instructions, which is the program. So the recipe that takes all these ingredients and on top of one core or maybe more core, if you need, to cook multiple things in parallel, can basically process the ingredients and generate the output, which is the food. We don't have time to go through this metaphor and everything, but I really like this picture that, for example, what if you don't have enough CPU or enough memory? I don't know if this has ever happened to you in your kitchen, hopefully not. But you have these cases where the kitchen counter is too small. You just can't fit all the ingredients there. You don't have enough burners to cook everything. And so this is also when things might start slowing down, or maybe where your process might actually die because you don't have enough memory and it gets killed. Another last thing that I want to mention, that sometimes people have expectations about clusters. Working in a cluster doesn't necessarily mean that it's going to be faster. And here there's a nice example that the laptop processing unit might actually have more power than the stove that has to share all the power with the multiple processing units. So often your laptop as a single processing unit is much faster than, let's say, that the same processing unit in a cluster, in a server. But of course, it's also kind of the compromise that on the laptop, you have only one or a handful of processing unit. In the cluster, you can actually run, thousands, tens of thousands of processing unit in parallel. But then again, what you need to understand is that is your code written in a way that can actually use the tens of thousands of processing unit, or is it that when you move it to the cluster, it will just use one processing unit, which is actually slower than the one that you have in your laptop. So all of this will be covered later with the example during the morning. And just the final picture, the GPU, I find it very funny. So where GPUs are like the burners, but in parallel, you can cook multiple, in this case, chickens. So it's a large system that at the same time can do the same operation multiple times. So hopefully this was, how can I say, inspiring enough and motivating enough. And maybe you all knew about these things. We don't really have time to cover this, but you can read this page, and there's even a video related to this page. But basically, this is what I was just saying, that, sometimes moving the stuff to the cluster doesn't automatically um, make things faster. So I'm basically ready to switch to pass or do you want to add anything, Susa, that might be good for clarifying?
No, I
Or
think you covered most things.
excellent. So I would also switch the screen to Richard and Simo, but do you want me first to explain a bit kind of the geography of the cluster, or will you go through, what is the login node then?
I think it's probably good if you would explain that.
All right.
So
So basically one thing, like you're all familiar with your own laptop or desktop, you log in with your username and password. And basically this is where you would be, that you have a desktop or you have a laptop. It can be in the Aalto network that you see here because it's in a office at Aalto, or maybe you're at home in the internet with your laptop. So then Aalto uses this virtual private network, and the idea is not to make your life more difficult. The idea is that once you know that your laptop, your personal laptop or your computer laptop are part of the network, then other bits that are inside the network also becomes accessible. The reason, of course, is kind of confidentiality of the information that might be moving between these different elements. And in general, it also makes it easier to prevent external attacks. So using the VPN in the end is useful, but of course there are also ways to connect to this system without necessarily being in the VPN. But for simplicity, let's say that now you're in the Aalto VPN, so now you actually have access to all these different elements that you see here. There are the department workstation, maybe you have one, or maybe they are given a laptop. We also have this type of external interface, vdi.aalto.fi, where you can basically get a virtual desktop. That's the VD, virtual desktop interface, so that you are, I don't know, out for a conference, but you don't have your Aalto laptop with you and you need to access something, you can always go to this vdi.aalto.fi and see the file system and the same thing that you will still see in the department. And then there's the Triton cluster. So the idea of the cluster is that there is another network inside the network, and this network between these hundreds of computers is actually very, very fast, extremely fast. It's called InfiniBand, and it's a type of connectivity between all these multiple computers that we have there, that it allows really quick exchange of information. Instead, if something from the Triton cluster would need to talk, let's say, with the department station or with the storage that is outside of the Triton network, things would already feel slower. The thing is that to enter the Triton cluster network, you need to go through the so-called login node, which is triton.aalto.fi. Now I put this sign there, which is for those who have a driving license, it means that you should not stop there. Even if you want to stop the car for a few seconds, it's not good. You need to move on. And the idea is that the login node is good for connecting to the cluster, running simple things, but then what you want to do is getting a dedicated node that is just for you with the resources that you need. Do you need a CPU, one CPU, many CPUs, a little RAM, lots of RAM, and so on? This will come clearer with the examples that are given in the morning and also later in the afternoon with the exercises. Then Triton has its own storage system, and the reason is this speed reason, that if Triton would try to access the storage system that you have in other Aalto computers, it would take the Aalto network down because all the I/O that is going on between the nodes and the external storage would be too much. So this is why we have a dedicated so-called Scratch storage system. The disadvantage of that, the good thing is that Scratch is huge. We have 5 petabytes of Scratch space, and it's also very fast to read and write. But the problem with Scratch that it's not backed up, and it's kind of the price to pay for having a huge and fast file system. So you understand that this is the similar kind of architecture is also in other computing cluster like CSC. So you understand that every time you kind of feel that your analysis is ready, it's time to move it out of the Scratch file system. Last thing that I want to mention is that we also have a kind of virtual desktop interface to the Triton cluster in this on-demand.triton.aalto.fi. So if, again, you are not with your computer or you need to visualize the files that you have generated or the picture, or it runs on Jupyter Notebook, then this is the website that you want to visit. And I think I covered everything.
Um,
Yep.
Enrico, maybe how do you actually get, if you want to move something out from scratch, how do you get it out?
Yeah, this will be, in my understanding, some of the examples in the morning. But basically, there are different ways. One way actually would be exactly this with this on demand, for example, that you can see the file system and get something out. But of course, there are all these other, in our documentation, we have, for example, you can actually, how can I say, make this file system visible in your operating system. So let's say that you have I don't know, Aalto Windows, you can actually make a scratch so that you see it with all the other letters of the disks that you have there. And then from there, you can basically copy some files out. So there's multiple different ways of getting data in and out of the scratch file system. And we will show a bit of those. But yes, that's a very, very important question that we often get. All right, so is there something to lift up from the notes document, or do you want to take the screen share?
There is some stuff there. I guess I can switch to the notes. Do you have the notes open on your computer, or should I switch there?
I should have them here.
Okay.
In the kitchen metaphor, what are the nodes we define for Slurm? Yeah, this is a good question. Maybe Slurm can be seen as the chef manager that coordinates all the other little chefs and in the multiple kitchens there are in this department, or in this apartment building. And I don't know if that's a good metaphor for, but I see that people are answering, so that's good. Is there a smart way to move data between Triton, Scratch, and department? Yeah, this will be covered and is partly covered. Yeah. All right. I don't think there's anything to mention. So maybe we can now switch to you, Richard and Simon.
Yes.